with respect to d, right? But this is same as a c times of the nu of
S6.
Sx of t. Agree? So see, what was our first claim that we needed to prove? We need to prove that this guy is immeasurable. Now think about it. I just shown that the integral of this is equal to the c of Sx of e. And the e is from the product sigma-algebra. So this is measurable. This is immeasurable. And you multiply it with the number, still immeasurable. So this integral is immeasurable. Okay. So integral is immeasurable. Hence I can say, let me conclude it, that x into this integral of Sxf related onto y d nu is immeasurable. Okay. So what is the next thing? The next thing is to just show the identity. So in order to show the identity, what I need to do? Just integrate both sides. Okay. So when you're going to integrate both sides, so integral of Sxf of y d mu, and you integrate it with respect to d mu. So you get what? You get c of the integral of nu of Sx of t actually d mu, right? Okay. Is it making sense? But we shown in the last second part that this guy is equal to second part. This guy is equal to c. Okay. C is c. So the product measure mu multiplied by nu operated onto. Okay. We got it? Can I write this guy in the terms of an integral? The answer is yes. If I integrate, okay, phi multiplied by the indicator function of e with respect to this d mu, and this is what this is your f d mu product. Okay. So you have this identity, but for what? Indicator function. So I'll quickly just finish up this proof. Okay. I know you must be tired. By the way, would that be a difficult task to extend this when f is not an indicator function but a simple function? Simple function के लिए extend करना मुश्किल होगा. Okay. We consider everything is going to be same. Let's consider the case to when f is, so I'll just do it quickly, okay? I'm not going to do S some EI actually, okay? Where the EIs are what? Are from again this the product sigma, okay? So what would be
section considered?
let me just directly write it. What will be the section of okay f section of f operated on the of y actually. Okay, so it's gonna be same as some okay, so it's gonna be so doing a similar kind of calculation is gonna be sum actually I equal to 1 to n, Ci indicate a function of sections of Pi. So that doing all calculations, but I hope you can make sense of it. So you're gonna get this. Okay. So if this is the case, then integrate it with respect to d mu. So this means that just integrate, so the integral is linear, so you can take it inside. Linear but for finite actually. But for infinite you have it, but under certain assumptions. Make sure that those assumptions are okay. You have it. So d mu. So this would be same as sum I equal to 1 to n Ci. The nu of the section of Eiz. Okay. And then, as argued previously, that this map is immeasurable. Okay, so this nu of the section is immeasurable. So multiplied by Ci is also immeasurable. So the sum is immeasurable. So this whole thing is immeasurable. And hence this integral, the map. Okay. So therefore, now you can integrate it once again. As x section of f of y, for example, d mu, and now I want to integrate it with respect to d mu. Okay. So if you're going to do it, what you're going to get? You need to integrate I equal to 1 to n, okay, of Ci, the integral of nu of fx of Ei. Agreed? Right? With respect to obviously d mu. Alright? And what was this thing? As I said previously, that this is same as sum I equal to 1 to n Ci, the product measure operated on the Eiz by part 2 of the last theorem. Okay? And then I can write this product measure as integral. Okay? And then I can say the same, the integral of the sum is the sum of the integral, and hence the same thing is true for the simple function. Okay? So I'm assuming this is true. Okay. You can do it for yourself. Let's do the really final part of this. How you can quickly extend it for the case of the general case actually. Let me end the knowledge there. It's hard work, but the payoff has been. Fubini theorem is kind of a theorem that we use all the time. We will need it in stochastic analysis all the time. So I want to compute the expectation of the integral of some function. So I'm going to say that okay, expectation is integral with respect to the probability measure, and that's an integral with respect to the Lebesgue measure. So you can switch it. So you can say that this is under certain assumptions the same as the integral of expectation. Actually, that's what would be something of that most interesting. Okay, the third and final part. Take F to be a general non-negative measurable map. So there exists obviously a sequence of simple functions, Fn, of simple functions So F is a map from where to where? So it's like product sigma-algebra to 0 to infinity. So these simple functions are also maps from product sigma-algebra to 0 to infinity. All this is true for them actually. Okay, simple function such that they increase to F actually. They increase to F. In other words, they are increasing sequence, non-negative as well, and the limit is basically equal. If this is the case, then we can show easily that the section of Fn would increase the section of Fn. Okay? The section of Fn would increase to section of Fn. It seems trivial, but it's worth verifying the statement actually. Okay? Why this is true. And if this is true, then so what does this mean? This means that I have an increasing sequence of non-negative functions that is converging to Sx. So it's a sequence of functions converging to Sx. So I am in the assumption of monotone convergence theorem. So the monotone convergence theorem implies that the integral of limit n goes to infinity of Sx of Fn with respect to t mu is converging Sx of f with respect to mu. So what was our first task? Show that this is measurable. It is measurable indeed. Why? Because this sequence of simple functions is measurable. And hence they are integrals. And hence this limit actually. So if this limit is measurable, this guy is measurable. Okay? Now, in fact, you can prove. In fact, I can show even. In fact, not only this is true, but I can also see that if Fn, if the section of Fn is increasing to the section of F, then this guy is increasing. It's not only equal to the limit, but is increasing. So in other words, so this sequence of integrals is increasing. It's non-decreasing and it's increasing to basically. Why this would be the case? Because you have this result. So then if f is less than or equal to t, then the integral is less than or equal to t. So if you have inequality in this sequence, then you must just integrate it. So you have this increasing sequence actually. Okay? So by monotone convergence theorem, this must be true. So now, what can I do? Okay. Can I apply again monotone convergence theorem? So see, what does this mean? This means that the limit n goes to infinity of Sx Fn d mu is equal to Sx f d mu, right? And then if I integrate again both sides with respect to, for example, d mu now, d mu and I can integrate it because these are immeasurable. There is no problem with it. Okay. And since this is an increasing sequence of a function converging to this, so the integral of the limit would be what? I can take this limit out actually. Okay? Can I take this limit out? Not Fatul's. So here's the thing. Just treat this quantity as Hn and this as H actually. So Hn is a sequence of measurable maps which is converging to H. Then again by monotone convergence theorems, okay, what can I say about by the monotone convergence theorem? Again by MCP, limit n goes to infinity, okay, of integral of Hn with respect to d mu would be the integral of h d mu h. And now for the you can substitute, okay, your value of Hn, which is Sx Fn d mu, okay, that is equal to Sx f d mu. Agree?
Yes, sir.
Correct?
Yes, sir.
By the way, what is the final thing? Very final thing. What can I say about this? So these are the sections of the simple functions. By the way, I need to put the d mu, and d mu here. Okay. Now we must be happy. By the way, what can I say about these guys? Equal. What can we say about these guys? So see, these are the sections of the simple functions, and you have this iterated integral. And for the simple functions, we have proved that the iterated integral is equal to what? The integral of that function with respect to
Fn.
So this would be same as saying that the limit n goes to infinity.
Integral of Fn.
The integral
Fn.
of Fn
D.
and d mu tensor product nu is equal to the same quantity. Okay? And then I can take this inside again by monotone convergence theorem. So if I take this inside monotone convergence theorem, then this is same as f d mu product nu equal to
The
thing that you want. Sx f d mu d nu. This is true by monotone convergence theorem. Okay. Now this way of argumentation, okay, so we're going to continue after the break. Alright, just make last remark. This way of argumentation is what? This way of argumentation is called that, okay, proving something for simple functions and then passing the limits. Okay? So I can say that the identity that I wanted to prove, I proved it how? I proved it for the simple functions and then passed the limits. So that's a hand wavy say of doing things. But when you want to really pass the limit, okay, you have to justify things that why you can do it. So it's not that difficult, but this is a method to prove things, for example. So we have proved it previously that, okay, you want to prove some identity, you show it for simple functions and then you show it that, okay, the same is true for the non-negative function as well, which is the limit of the simple functions, okay? So,